Hi guys, my name is Daly, and I'm tag teaming this presentation with Fiona.
Hi Lee, nice to meet you.
And so we're going to talk about compression in DPDK. And this is going to be kind of a hard and fast presentation at a high level because it's one of the first lightning talks that we have here. If you have any more fine-grained details that you'd like to find out, you can find us after or look for the guy with the tie. So how to deflate your data with DPDK? What we're going to start off with is the why. Why do we do this? And then we'll talk about the what is it and a little bit of detail of how we did it. After that, we'll talk about the API and the PMD. And then last steps, we'll talk about our next steps. Where are we taking this? Where are we going next? Some asks from the community. So to talk about why we added this to DPDK, we've taken a little bit of a step back. When DPDK was first around, it took packets from the NIC, did some work in a performant way, and sent them out again. As time went on, it did that, and it did very well. But then security became a talking point, so crypto dev was added. And now big data is a talking point, so compression is added, and storage. There are big topics on people's lips. So the two main use cases are networking storage, and then just general storage. So for networking storage, if you can reduce the amount of data that you put on the network, reduce that load, it's a good thing. If you can reduce the bandwidth that you're using, again, a good thing because IoT is sending out so much data these days. And then just general storage. When that data gets sent across the network, if it's put anywhere in the cloud, you want to reduce that footprint as much as you can. Now, for those two use cases, there's different types of compression. You stateful and stateless. For the use case where you have data being sent over the network, and you may not have all that data at one time. You can compress what you have, keep the state, and then as you have the rest of the data, compress that, and it will keep those states as you compress your data. For the stateless, where you already have it stored, you can just compress all of that in one go. And then why in DPDK? The users wanted a generic API that they could use, and if you were already using DPDK, why use a middleman? We can now just do compression in DPDK itself. So this is a collaborative effort with Intel and Cavium and NXP, and we've also been working closely with SPDK, who are going to consume this API, and they're going to start to integrate this really soon, and Fiona's going to work with that. So I'll hand you over to Fiona.
Okay. So I'm going to talk about the key features of the API and also the design decisions. So if you click on the next slide there. Yeah. So actually, I won't talk about, there's a couple of different key design decisions here, and I'm going to focus on the second one, which is about the private transforms and streams. So, and the other ones you can come and ask me about afterwards if anyone has any questions. We started off copying essentially crypto dev because that was one of the questions, will we even put it into crypto dev? But then we went with compressed dev, and we had sessions because crypto dev had sessions, and it seems like a good way to pre-do some work before you get onto the data path. But then, because we were in compressed dev and it was separate, once we got into the discussion of how we'd use it, we realized that sessions, first of all, they didn't sit very well in compression, because sessions, when you think of security, tend to be, crypto have a key, and they're a group of ops that are associated together, and they all share the same key. When it comes to compression, the transforms that we're passing in specify things like what algorithm you want to use, which is Deflate or LZS, whether you want to do a checksum or not, what level you want to do. And you can do many operations using that set of transform parameters, but those operations are not necessarily associated. They're not from the same file. So you might need the same transform for many, many different operations. And they're not really a session. That concept of session didn't seem right. So we invented something called a private transform. So the transform has the parameters you want, like will I do a checksum, what level, what algorithm, and a PMD converts that to a private transform where it sets up the data whatever way it wants for its own use to be more efficient on the data path. But then that private transform made sense for a stateless operation. So at the moment, so Lee already referred to stateless versus stateful in compression. And this is something we, again, that is a concept we didn't have in crypto. But for compression, a stateless operation is where you have, as I said, all the data, you give all the data in one operation, and you get your results back, and it's compressed. You go away, you can decompress that. When you get streams of data, which would typically be used in zlib or ICL, or most compression engines have that concept of stateful. It's where you said you don't have all the data. You want to send a batch of data down, get that compressed. The follow-on data is related to the previous set of data, because that original data, the way you do compression is you look for patterns. and you match those patterns, and then you store smaller markers to be able to take less space for that amount of data. So you want to maintain history. So you send an operation down, you see a certain pattern. The next block of data you send down, you see another pattern. So yeah, to cope with that idea, you have to maintain history. So we didn't think that the private transform was a good place to do that, because the private transform is very much something that you just use and doesn't maintain any state. It can be used across many different operations. So we invented something called a stream, an RT comp stream, and that's equivalent to a private transform plus some state data about the operation. And it's distinctly different behavior, because with the stream, you can only have one at a time. So each operation depends on the previous operation, so you can do sequentially one operation at a time within those streams. So we separated them into two different structures. So that's kind of one of the key kind of architectural differences on the API from, say, crypto. So the other two things I won't go into, we'll talk a little bit about mBuffs later. You can click onto the next slide, please. Okay, so some of the key features, again, we have probably mentioned most of these already. Actually, most of them fairly obvious. We've got the asynchronous API and a burst API, so that you can amortize your load over when you send off something to a hardware accelerator. You want to be able to go away, do some other work while the work's being done by the hardware, and then come back and collect it later. So that asynchronous API was a bit different than what current users of compression would be used to. So we need to kind of train them into using that idea. So that's the next step. We'll be doing that in future. Chained mBuffs. So yes, mBuffs have at the moment a limitation of a UN16 for the data size. So that's a maximum of 64K minus 1, which for many packets is a perfectly reasonable size. But for compression, obviously, you may want to compress a large amount of data. So we're using chained mBuffs. There's a couple of algorithms, Deflate and algorithm LZS. Most of the PMDs using Deflate. That's the most standardly used algorithm. Compression levels are standard in any compression algorithm. They give you a trade-off between ratio and speed. You want to compress faster, you don't get as good a compression ratio. You want a really good compression ratio, you've got to take a little bit more time, and so you go for a higher level. Okay, some of the others, we can generate hash and checksum generation, and they're both about authenticating the data. Okay, so that's a fly through the features that we've got on the API.
Yeah, and then to talk about how the API actually fits into the DPDK framework itself. So if we see here, we have an application that will utilize our compressed dev APIs. And they're generic, most of them are generic APIs, your device management, your stats capabilities, and then we have your stream/private transform management. That's what Fiona was mentioning earlier, whether you're doing stateful or stateless, which will depend on your use case. We have operation management. This is similar to crypto devs, and this will contain some of the more generic information that you will need to do that compression operation, aka where is the data that I want to compress, and where do I store it when I'm finished compressing it. And then we have our normal burst APIs. Now that level is independent to our PMDs that we have here. So we'll talk about them a little bit later as well, but we have 2 software PMDs and 2 hardware PMDs. And now take a little bit of a closer look at that actual application itself. So the top line is the usual flow of an compression application in DPDK. You allocate memory, you set up your devices, you do general config. But our last step there, creating that private transform. Again, that's what Fiona mentioned, where at the API level, we have a generic transform, and that's what the application will fill in. And then that gets converted into a private transform, which is PMD specific for that algorithm. What is that individual information that the algo needs? And then we come into our main loop, and that's what you will keep repeating, because you will use that transform for all the ops that you need to do. So you allocate your ops, you build your ops. That's where the application will just say, okay, here's the data compress, and here's where you put it when it's compressed, as well as offsets, etc. You enqueue, dequeue, we all know what that is, and free your ops. And that's your repetition loop to get through all your data. And then your usual, free your transform, stop, and close the device. So I'll hand you back over to Fiona again for the PMDs.
Okay, this is just a quick look at the 4 PMDs that we've got. And as I said, we started off doing a couple of proposing this API and wanting to plug in an Intel hardware accelerator underneath it, and a software library which runs on Intel, which is the ISA-L library. So we've got 2 PMDs for those, one for software offload and one for hardware. The Quick Assist, Quat is Quick Assist there, the Quick Assist family of hardware accelerators. And Cavium came on board, and they helped work the API with us, and then they also plugged in a zlib PMD, which would use the zlib library, which is probably the most commonly used compression library, and that will run on all CPU architectures. And they plugged in their own Octane-X PMD to work on their hardware libraries, our hardware accelerator engine. So we have 4 PMDs at the moment, and I don't know if there's anyone else planning to put one in, but we'd be delighted to see other people plugging in other compression engines underneath this.
Now, lastly, our next steps. What are we doing next? So, performance tool is going to be put in 1811, and the main qualities that you look for are throughput and compression ratio. So, how much can you compress, and then how good can you compress that data? API changes. So perhaps an alternate type of MBUF. The attributes of an MBUF don't typically lend themselves well to compression. The size, the 64K max size, and also that if you already have your data stored, you don't have to copy that into an MBUF, which is not ideal. We're going to try and remove, or we are going to remove the experimental tag that this API has. And then future developments, maybe an ask from the community. A sample application, and as well as that, stateful in a PMD. All the PMDs implement stateless at the moment. So like Fiona was saying, even another PMD that could do stateful, because the API does support it, so it'd be nice to have a PMD that implements it. And that's it. That's a compressed version of our slides. Any questions?
Viewed as storage?
Yes.
Yeah.
So from our purpose, storage had expressed a lot of interest in this, so yeah.
Because if someone wanted to implement, say, IPComp here, you probably want it in the...
Yeah, and it's absolutely, I mean, the API is designed to, obviously, networking is important. We think the main use case is storage, but we, and Cavium in particular, were interested in IPComp, and the stateless, the stateful flow would support that. Yeah.
Did you change the RTM buff for your experiments, or you came up with kind of a configurable RTM buff?
We're using the MBUF exactly as it is, but we, the storage team and our storage stakeholders aren't very happy with that idea. They want to say their data is somewhere else. So one of the things we could do is change the RTM buff and change that uint16 to uint32, for example, or find some other. But I'm quite interested in the follow-up talk after this one, where we have the MBUF pointing to external data. That might be just the solution we need for storage. But there was another proposal as well that in storage they have structures they already use that are common to the storage community. Maybe we'll plug those structures in directly into DPDK. That's got to be explored in the next few months.
Mm-hmm. Because I think there was already an idea also to make RTM buff configurable. So depending on the features you want to use across your own system, you can come up with a smaller or tailored RTM buff. And if it has kind of a versioning or it has its own feature set, and the two parties can communicate and they can negotiate kind of the usage of the RTM buff.
Yeah, that certainly could be looked at.
Thank you.
Thanks.
Okay, thanks guys.
Thanks.